First of all, thank you to the organisers for allowing me to speak. It's always a pleasure to come back to Manchester. This is where I spent time as a student. Unlike the last speaker, I'm old enough to have shared the earth with Jim Wilkinson, but I never got to meet him. My mathematical career started a little bit too late, but I worked here with Nick, and Nick instilled in me many of the values that Jim Wilkinson had. During my thesis, one of the most important papers for me was one by Golub and Wilkinson, ill-conditioned eigensystems and the computation of the Jordan canonical form, solving a very tricky problem to do accurately, and this was very helpful in the work I did in my thesis. But I'll move on and talk about a problem in perturbing doubly stochastic matrices. This is a problem in linear algebra working with these doubly stochastic matrices that I've devoted more time than I should have, perhaps, and maybe many of you have not spent any time doing this, so it may seem a little bit esoteric, but I think it's of great value and has many applications. I'll outline one particular application, but if I have time, just at the end, I'll talk about some rounding errors that appear in an algorithm which is much more familiar to most of you, and you can tell me whether I'm right to object to these rounding errors and their manifestation. But anyway, let me move on to the main business of my talk. And what I want to do is I want to take a matrix, a non-negative matrix, and all I'm looking for are a couple of diagonal matrices, D and F, so that when I apply these to the matrix A, the matrix P that I end up with is doubly stochastic. Statisticians, probabilists may object to me calling it doubly stochastic because I'm not using it in a probabilistic setting, but for me is the rows and the columns all sum to 1. So it's an object that you're probably well aware of and familiar with, even if you don't work with them every day.
What does greater than or equal to 0 mean here?
Every entry-wise, yes, so a non-negative matrix. And it's been well known for 50 years what the conditions are for the existence of such a scaling. In particular, if a matrix is fully indecomposable, then there is a unique up to a scalar multiple, a scaling of this form. So fully indecomposable, if you're not familiar with that term, is just a generalization of irreducibility. So you know a matrix is irreducible if you can apply a permutation either side and reduce it to a block triangular form. For indecomposability, you are allowed to apply a different permutation to each side. So irreducibility, you're looking at a symmetric permutation here. You can use a different one on either side. And this unique scaling and up to a scalar factor, this will become relevant later on as well, if I get time to talk about that. There are also multiple scalings if the matrix has total support. So total support means that if you have a non-zero entry, then you can always permute this onto a positive diagonal, a diagonal of all positive entries. And we can think of this in terms of a block diagonal structure will have total support. That again is going to be important because because the application I'm thinking of is trying to find a block structure within a matrix which doesn't have a perfect block form, but hidden away amongst its entries is something that's nearly block structure. And so this is where my perturbation analysis is going to come in. I'm going to look at the results, or some spectral results for the perfect block structure and try and apply them when I don't quite have this block structure, and is this justified? So here are the particular points which are important to me for a doubly stochastic matrix. So suppose I've got a square matrix, it's fully indecomposable and it's doubly stochastic. Then it's trivial to show that its principal singular value, so here we're thinking of a non-symmetric S, we can think of eigenvalues and eigenvectors for the symmetric case, which is usually sufficient for what I want to look at. But it has a principal singular value of 1, its multiplicity 1, the associated singular vectors on the left and right are just vectors of 1s. You know, this is all quite clear if you have a doubly stochastic matrix. If you have a doubly stochastic matrix which has block diagonal structure, each of these blocks being fully indecomposable, and therefore your matrix S having total support, then this singular value has multiplicity k. And so what we're going to do is to partition a matrix according to these blocks from the, or to find the block structure using these singular vectors, partitioning according to where the ones appear in my singular vectors. Now, if any of you know about Fiedler vectors, which I know a lot of you do, this may ring a bell. It's akin to using Fiedler vectors. But what I'm going to do is try and be really, really greedy. I'm just going to compute one single vector and try and discover as many blocks as I can. And so I've been working on this with some colleagues, and with some bells and whistles attached, we've had some success doing this. But the idea is as follows. If there are a number of blocks, k blocks, then if I compute a singular vector using your favorite singular vector algorithm, then it's going to be made up of a combination of these individual basis vectors, and because of the structure of these basis vectors, I can split this into pieces because it will be piecewise constant. I can reorder this into a piecewise constant vector and therefore find the block structure. Now, this may work, it may not work, but in some cases it works very well. So here we have a toy example just to indicate the potential of this method. On the left, I've used, so this is, think of this as the pattern of a network, of a graph, and on the left we've got the graph Laplacian indicated with the dots there. Yes, so now for now I'm just working with symmetric matrices, yes. So we've got an undirected graph. I've computed the graph Laplacian, and we can, in theory, use the Fiedler vector to split this into clusters, or to partition this. There are 3 almost clusters in this thing, and if I use the Fiedler vector, you see we almost see that structure in these eigenvectors of the Laplacian. These are the 2 non-trivial eigenvectors of the Laplacian, but if we order these by size, it becomes less clear where I should partition this. So imagine I'd scrambled this matrix up. How would I unscramble it? It's hard to do with these eigenvectors. But with the doubly stochastic scaling, you see it's easy to split this because this piecewise constant structure is so apparent. So it would be lovely if this always arose in practice, but of course in practice things aren't quite so simple, and so we have to do various other tricks in order to try and reveal some sort of structure. But anyway, let's get on to the perturbation theory before I run out of time. What am I wanting to do? Okay, so I've got a matrix A. We're going to assume this has got perfect block structure. Okay, I can find a scaling to turn it into a doubly stochastic matrix. Now I've got an almost block structure. So I've got a matrix A tilde, which is a perturbation of this pure block structure.
Do you perturb within the set of stochastic matrices, or do you...
No, this is before the scaling. So A is just, A is non-negative in this case. And so yes, H here is a matrix of norm 1 in whatever norm you want, and it's non-negative as well, let's say. And then we've got a parameter epsilon. So the question I'm going to ask is, how does the scaling of A tilde relate to the scaling of A? Okay, so ideally we'd like A to be block diagonal, so it has this perfect structure. There's a problem there because I want to assume full indecomposability, this condition I spoke about earlier. So let's assume it has this, so it won't have block structure to start with, so my theorem will be true, but it won't be true for the cases I'm particularly interested in. And what I can do is I've got a constructive theorem that tells me the following. There is a perturbation of P, the scaling of A, which is close to doubly stochastic in the following sense. If I scale P tilde using two more diagonal matrices, F and G, and F and G are very close to being the identity matrix. So E here is a vector of 1s, the vectors F and G are very small vectors. Then this scaling applied to P tilde gives me something which is almost doubly stochastic, in the sense that the error there that I have, if it were perfectly doubly stochastic, Fp tilde GE and the G P tilde transpose F times E would both equal 1. Those are the row sums and column sums. The error is of order epsilon squared. So we can show then that in certain cases, depending on this matrix Q and also on properties of P, that a small perturbation results in a small perturbation of the doubly stochastic factor. Okay, there are issues to deal with. The principal issue is when we write this and try and work out what these vectors F and G are explicitly, we end up with a system I, P transpose I. P has an eigenvalue equal to 1, and it turns out that this matrix is singular. So trying to find F and G is a problem, but we can show this is consistent because we know about the multiplicity of this eigenvalue 1. We can find the kernel explicitly. So that's lovely, but it's not the case I'm interested in. I'm interested in the case where A has lots of blocks individually. And so what we've been able to do is to extend this analysis to that particular case. Okay, yeah, I'll come back to interpreting this result later on. Okay, so we need to extend our analysis because we want to consider this block structure. The issue is then that P sim, this matrix I, P transpose I, is even more singular. It has a kernel of higher dimension. But we can, using the fact that the scaling is not unique, but unique up to a scaling factor, manage to write down the kernel of this new matrix and to show that our system is still consistent. So we can work through and work with the block structure that I was after. This is just for 2 blocks, but we can work recursively on more and more blocks. Okay, I need to interpret that result. Okay, so I've shown that some quantity is small if F and G are small. When are F and G small? Well, it's true if Q is constrained, if the norm of Q is constrained in some ways, and we can give conditions on that, and the eigenvalues of P that are not equal to 1 are sufficiently far from 1 that this perturbation makes sense. We have got arguments as to why that is what we should expect if our matrix A or A tilde is close to having block structure. So we've established this result, this perturbation result, as follows, that a small perturbation to the original matrix A results in a small perturbation to our doubly stochastic factor. Okay, I rushed through that a little bit because I think of more general interest is the following picture. So there's a Rorschach matrix for you in the bottom right-hand corner. What do you see in that matrix? What you see depends on where you're brought up. You know, I see a little bit of a frog in there, but in fact, this is rounding errors. Okay, so I'm sure that's what you all saw yourselves, being this audience. Again, I've got a graph. This graph at the top left, it's not a connected graph, and what I want to do is to find out the connected blocks. So what I want to do, as a lazy linear algebraist, is just form the matrix exponential. The non-zero entries of this matrix exponential will tell me where the links within this network are. And the non-zero structure of the matrix exponential should look like that. But when I use my favorite matrix exponential algorithm, or just go into MATLAB, I get the following picture. All this zeros are destroyed by the algorithm that's going on within MATLAB. Not only that. Sorry, no, I'm just computing.
Oh, you're not trying to reorder.
No, this is a different problem. I'm just trying to find the connected blocks within this network just by forming the matrix exponential. Okay, so it's a lazy tool for doing it, But not only does this matrix fill up with lots of tiny entries, those non-blue entries, whatever color that is, are negative, okay, which is not a great start when I started with a non-negative matrix. Now, I know I'm being a bit demanding, asking for all the zeros to appear where they are, but am I being too demanding, asking that when I start with a non-negative matrix, that the matrix exponential computed by any particular algorithm should be non-negative as well? Clearly, from the Taylor series, it should be non-negative, if you just think of it in terms of the powers of my non-negative matrix A, but I will leave it there because I've run out of time and let you tell me why I'm being too fussy. John.
There are very good direct methods for finding block structure of a sparse matrix. Have you considered using them?
Oh, yes, I know I'm being lazy here. So by using those methods for finding the block structure, I could correct the matrix exponential. Is that worth considering? You know, if the matrix exponential is going to give me negative entries when there should be no negative entries.
I was a little confused. I didn't quite. You started out with saying you want to rescale, right?
Yes.
To a doubly stochastic matrix. So how is that
Oh,
related?
this is just a lanyard. This is a bonus for everybody who doesn't deal with doubly stochastic matrices. Yes.
So there's a very important practical problem where you would need that. That there's doubly stochastic stuff that is to finding the structures in a molecule and where there's binding and non-binding. But there, the problem is that you need that your perturbation is in the class of, so that A plus epsilon perturbation is against stochastic. And that's a completely crazy class. Right. And that's a really big open problem if you have a stochastic or doubly stochastic matrix. What is the class of perturbations that you're allowed to do, and are these the perturbations that you're really living with? So have you looked at that?
No, I've got this far. So yes, I want to compare one doubly stochastic matrix to another. So this is an incremental result which shows if I go, I start with a non-stochastic matrix, make it stochastic, and I make my perturbation outside of that set. How close do I end up when I come back there? So whether there's a route from your problem or not, I can only speculate.
Okay, I think we'll thank Felix for his talk.
Okay, thank you.